Hello everyone, my name is Siddharth and I am from Chanakya section. So our topic is about data structures and algorithm. So we are starting about data structure and algorithm. Here an introduction. So this presentation provides an overview of the key concepts covered in the chapter 1 of data structures and algorithm. A comprehensive guide to designing and analyzing algorithms. We will delve into the fundamental principles of the algorithm designs, exploring the transition from problems formulation to program creation, the essence of algorithms themselves, and various methods for equating their efficiency. So, from problems to programs, the algorithmic journey. So, problem formulation. The initial step involves understanding the problem clearly and defining its specific requirements. This includes identifying the input, output, and constraint associated with the problem. So, mathematical modeling. Once the problem is understood, it's crucial to model it using appropriate mathematical tools. These steps help formalizing the problem and allow us to apply algorithmic solution effectively. So, third, algorithm design. With a clear mathematical model in place, we can design an algorithm to solve the problem. This involves choosing appropriate data structures and developing a sequence of instructions that will produce the desired output. Fourth, the program implementation. So the algorithm is then translated into a computer program using a specific programming language. This step involves writing code that effectively implements the algorithmic instructions. Last, the testing and validation. So once the program is written, it's crucial to throughout test is with various inputs to ensure it functions correctly and proceeds accurate results. These steps help identifying and fix any errors or inconsistency in algorithm or its implementation. Algorithms, the foundation of computation. Finite sequence of instruction. Algorithms are defined as precise set of instructions that specify the steps needed to solve a problem, and each step must be executable in a finite amount of time. Well-defined instructions. Each instruction within an algorithm must be ambiguous and clearly defined. This ensures that the algorithm can be executed consistently and produces the same output for the same input. So finite transmission. Algorithms are designed to terminate after a finite number of steps. This ensures the algorithms will always produce a result in reasonable amount of time. So, power of mathematical models. Graph theory. Graph theory provides a powerful tool for modeling problems involving relationship between objects. For example, traffic lights. Design can be modeled using a graph where vertices represent turns and edges indicates potential conflicts between turns. By analyzing the graph's properties, we can design optimal traffic lights patterns. So that set theory. Set theory is essential for modeling problems involving collection of elements. For instance, when the dealing with a database of customer records, we can use sets to represent group of customers based on the shared attributes. Other mathematical tools. Other branches of mathematics, such as linear algebra, calculus, and probability theory, can also be used to model problems and develop efficient algorithms. Each mathematical tool provides a unique perspective and framework for understanding complex problems. Equating algorithm efficiency. Worst case analysis. Worst case analysis focuses on the maximum amount of time or resources an algorithm might require for a given input size. This approach ensures robustness and help guarantee that the algorithm will perform acceptably even in the most challenging scenarios. Average case analysis. Average case analysis considers the average amount of time or resources an algorithm needs. Overall possible inputs of a specific size. This analysis provides a more realistic estimate of the algorithm's typical performance. Best case analysis. Best case analysis examines the minimum amount of time or resources an algorithm might require for a given input size. This analysis is less practical in real world scenarios but can provide insight into the algorithm's potential for optimal performance. Time complexity and growth rate. Big O notation. Big O notation is a mathematical tool used to describe the growth rate of an algorithm running time as the input size increases. It provides an upper bound on the algorithm complexity, allowing us to compare the efficiency of the different algorithms. Logarithmic complexity. Algorithms with logarithmic complexity typically perform a constant amount of work for each half of the input size. These algorithms are highly efficient for large inputs. Linear complexity. Algorithm with linear complexity performs a constant amount of work for each element in the input. These are relatively efficient, especially for smaller inputs. Quadratic complexity. Algorithm with quadratic complexity performs an amount of work proportional to the square of the input size. They become less efficient as the input size increases. Exponential complexity. Algorithms with exponential complexity performs an amount of work proportional to raised to the power of the input size. These algorithms insufficient for the large inputs and are typically avoided for the practical problems. Abstract data types. List. Description. A linear sequence of elements where each element has a specific position. Operation. It used in insert, delete, search, access by index. Set. An unordered collection of distance elements where order and repetition are not significant. It is also used in insert, delete, search, membership test. A collection of vertices connected by the edges that represent connection between the objects. It used for adding vertex, adding edge, transfers, search for the paths. Tree. A hierarchical data structure where elements are organized in tree-like structures with a root node, branches, and leaves. It is used for inserting, deleting, searching, and transfer, and also finding minimum and maximum. Practical consideration for algorithm choice. Efficiency versus simplicity. While efficiency is important for large-scale problems, simpler algorithms may be preferable for smaller problems or in case of implementation is a priority. Time constraints. The algorithm execution time is a crucial factor, especially for real-time applications. Choosing an algorithm that meets the time constraints is essential for delivering optimal results. Memory usage. The algorithm memory footprints is also an important consideration, particularly when dealing with limited resources. Algorithms that uses less memory are often more efficient. Easy implementation. The complexity of implementation an algorithm can impact the development time and effort required choosing the straightforward and saving the development resources. Recursive algorithms, a powerful tool. Self-reference. Recursive algorithms solve problems by breaking them down into smaller, identical subproblems and then combining the solution to subproblems to arrive at the final solution. Base case. So each recursive algorithms must have a base case that stops the recursion. This base case provides a terminating condition, preventing the recursion from the continuing identify. Recursion relations. Recursion relations are mathematical equations that express the time complexity of a recursive algorithm in terms of the size of the input and the time complexity of the recursive cell. Exploring further advancement concepts. Chapter 1 of Data Structures and Algorithm provides a strong foundation of exploring advanced topics. As you develop deeper into the field, you will encounter more complex algorithms and data structures, such as dynamic programming, greedy algorithms, graph algorithms, and advanced sorting and searching techniques. These concepts are essential for tackling challenges, computational problems, and optimizing software performance. So, thank you. Please like and subscribe.
Yeah.